Let us see this problem. We are given an integer array. We need to find out maximum sum of a circular subarray. A circular subarray includes normal subarrays, also the subarrays which are formed by connecting the last element back to the first element. Let's see this example to get a better idea. Let's say we have this array 10, 5, minus 5. The normal subarrays of this subarray are 10, 5, minus 5, then 10, 5, then 5 minus 5, then 10, 5, minus 5, all three elements. So these are normal subarrays that we have been seeing so far. Now, these circular subarrays also include the subarrays which are formed by connecting the last element back to the first element. For example, minus 5, 10, 5 minus 5, 10. This is also a subarray. Minus 5, 10, 5. This is also a circular subarray. So these are all possible circular subarrays of the given array. So we have normal subarrays also, and we have only circular subarrays also, which are only circular. So circular allows both normal and subarrays formed by connecting the last element back to the first element. Now our question here is, we are given such an array. We need to find out maximum sum of all circular subarrays, which means we are going to consider these subarrays and these subarrays, and out of all these subarrays we need to find out maximum sum. Now if you see all these subarrays, the sum of this is 10, this is 5, this is minus 5, this is 15. So this is highest actually of all these subarrays here. This is 0, this is 10, this is again 10. And you can notice that if you consider all elements, they are having the same value, right? This sum is same, this sum is same, only the order is different. And the sum of this subarray is 5. So out of all these, this is the maximum sum subarray. So our return value for this input is going to be 15. Let us see more examples to get better idea of this problem. Let's consider this array. The maximum sum that we can get is 12 by considering this circular subarray 3, 4 and 5. You can try generating all these subarrays which are normal subarrays and as subarrays obtained by connecting last element back to the first element. Out of all these, we get the maximum sum as 3, 4, 5, 12. Let's see this. In this we get the maximum sum as 2 plus 3, 5. Let's see this example. In this example, we get the maximum sum as 8 plus 4, 12. We can't get more than 12. For example, if I consider these two elements also, I'll get minus 2 added to it, which will reduce the sum to 10. So 12 is the maximum answer. Let's see this example. In this example, we get the maximum sum as 10. And this is not a subarray which is obtained by connecting last element back to the first element. It's a normal subarray, right? And we're getting a maximum sum from a normal subarray here. Let's see this example. Again, we are getting maximum sum by considering normal subarray. Let's see this example. Here we are getting the maximum sum by considering a subarray that connects last element back to the first element. So our subarray is 7, 3, minus 4, 5, 6. And sum of this subarray is 17. Now please pause this video and try to think of an approach that takes an array as an argument and returns the maximum sum of a circular subarray possible for this array. Let us see the naive solution first, a solution that takes big O of n square time. The idea is to consider every array element as the beginning element, find out the maximum sum that you can obtain by considering this as a beginning element. Every subarray, whether it is a normal subarray or circular subarray, has to begin with some element, right? So from every element, we find out all the subarrays, we find out their sums and store the maximum of all these sums for every element. And ultimately, our final result is maximum of all these maximum sums. So we run a loop, I equal to 0 to n minus 1. Current maximum stores the maximum sum that you can obtain when ith element or element at index I is the beginning of this subarray. And how do we find out the maximum of all these subarrays that begin with array I? We initialize the current max, we initialize the current sum. Every element that we add to the subarray, we update current sum equal to current sum plus index. So for every element, there can be n subarrays that begin with it. This happens only in circular case, right? Because in circular, you can move back and then have a subarray. For example, I equal to 0. The one subarray is array 0 itself, 5 sum. The second subarray is 5 minus 2, 3. The third subarray is 5 minus 2 plus 3, which is 8 minus 2, 6. The fourth subarray is 5 minus 2 plus 3 plus 4, which is total sum 10. So the maximum sum that we can get with 5 as the beginning of a subarray is 10. Now let's see minus 2. The first subarray that begins with minus 2 is minus 2 itself, with sum minus 2. The second is minus 2 plus 3, 1. The third one is minus 2 plus 3 plus 4, 7 minus 2, 5. The fourth one is minus 2 plus 3 plus 4 plus 5. The sum is 10. So the maximum sum that we can get when minus 2 is the first element is again 10. But there are 4 subarrays that begin with every element. From 3 there are again 4 subarrays. 3, 3, 4, 3, 4, 5, 3, 4, 5, minus 2. Right? So we traverse through all these subarrays. We use modular arithmetic here. We run a loop for j equal to 1 to n minus 1 to find the next element in the subarray that begins with array I, and this index is computed using modular arithmetic so that you can find total n subarrays in circular way. Using this index, we find the current sum and then we check if sum of the current subarray that begins with array I is greater than the overall subarrays that you have found that begin with I, right? You take the maximum of all these, and once you have found the maximum of all these subarrays sums that begin with array I, you compare this maximum with the result, and if result is less than that maximum, you update the result, and at the end you return the result. So the idea is simple. For every element, find out the maximum sum of a circular subarray that begins with this element. So when I say circular subarray, it means normal subarray as well and circular subarray, right? And ultimately find out maximum of all these maximums and return this. So in this case, if you consider 5 for I equal to 0, you will have the maximum sum as 10 when we have 4 elements included. Your current sum will first be 5, then it will be 3, then it will be 6, then it will be 10. And your current max will be updated to 10 because that's the maximum. So your result, which was initialized as array 0, you will update the result as 10. Now you begin your loop for I equal to 1. Your current sum will be minus 2 first, then it will be minus 2 plus 3, 1, then it will be 1 plus 4, 5, then it will be 5 plus 5, 10. So you're getting the current max sum as 10 for minus 2 also. It's not greater than the result, so we don't update the result. Now we begin with 3 for I equal to 2 and value 3. So we are getting the current sum as 3 first, then 3 plus 4, 7, 7 plus 5, 12. 12 is greater than result, right? And 12 is the maximum sum that you can get with 3. All sums that you are getting are 3, 7, 12 and 10. Out of these, 12 is the maximum. And this is also more than the result, so we update the result also. Now we try for I equal to 3 and what we get as a maximum sum, again 10, which is not greater than the result. So our result remains 12 and we return the 12 value. The idea is really simple and has big O of n square time complexity. Now please pause this video and think of an approach that works in big O of n time. Let us see the efficient solution now. The idea of this efficient solution is to find out maximum of these two values. The first value is maximum sum of a normal subarray. Normal subarray means a subarray which is not obtained by connecting last element to the first element, right? And maximum sum of a normal subarray can be computed using cadence algorithm. We have talked about this algorithm in this problem in a separate video. So this is first part. The second part is maximum sum of a circular subarray. A subarray which is obtained by connecting the last element back to the first element. A subarray like this, which has certain elements from x0 to xi, then some elements from xj to xn minus 1. How do we find out maximum sum of such subarrays? If we can somehow find out this maximum sum and find out this maximum sum, our final output will be maximum of these two, because in the result it can be a normal subarray or it can be a subarray which connects the last elements. So how do we find this part? If we find this part, then we have solved the problem. We can find this using cadence algorithm. We can, if somehow find out this one, we simply return the maximum of these two. We can actually find out this part also using cadence algorithm. Please see these examples and try to find out a pattern to find the maximum sum of a circular subarray, a subarray which connects last element back to the first element. In this example, we have these three elements considered. In this example, we have these two elements considered. And in this example, we have these five elements considered. Now, if we talk about general solution, we are going to find out a maximum sum which includes some first elements and some last elements and does not include some middle elements. Do you see any property about the middle elements which are not included? These elements actually are the minimum sum subarray, minimum sum normal subarray of the given array. So the idea to find out maximum sum circular subarray, this part is to find out minimum sum subarray using cadence algorithm, using modified cadence algorithm, and subtract this sum from the overall array sum. If you have overall array sum and if you subtract this sum, you will get this part, the maximum circular subarray sum. Let's see these examples to understand this. In this array, minimum subarray sum is -2. And if I subtract it from the total sum, I'll get the required sum, which is sum of 3, 4, 5. In this example, minimum subarray sum is -4, 3 and -5, which is -9 plus 3, -6. If I subtract -6 from the total array sum, I'll get the required sum 12. In this array, minimum possible sum is -8. If I subtract this -8 from the total sum, I'll get these elements. So that's the idea to find out overall result. We find out this using normal cadence. We here apply again cadence. We apply cadence to find out the minimum subarray sum and we subtract this from overall sum. That's how we find out circular subarray sum. Please note that this circular does not have to be the maximum, does not have to give you the maximum circular sum. But if there is a circular sum which is maximum, it's going to give you. It's going to find out the minimum sum and subtract those from the overall sum and going to give you the circular sum. Once we find out these two, we return the maximum of these two. Now please pause this video and write a program that implements this approach. Let us now see implementation of this efficient approach. So first part of this code is normal cadence algorithm, standard cadence algorithm that we are going to use to find out the normal maximum sum and also the circular maximum sum. So we have written function for this. Now this is our main function where we find out the overall maximum, which considers both normal subarrays and circular subarrays. So inside this function, we first compute max normal, which is maximum of a normal subarray, which is simply computed using cadence algorithm. After that, we have this check. If max normal is less than 0, it means all the elements in the array are negative. In that case, we can simply return max normal, because if everything is negative, then this function is going to give you the largest value, right? Which is minimum absolute value of a negative number, right? So we do not proceed further if max normal is less than 0. Now here we find out circular sum, which is maximum sum when you are considering corner elements as contiguous, first after the last. For that, we just talked about, we need to find out minimum sum subarray, but instead of modifying this function for minimum sum subarray and writing it again, what I have done in this code is, I have inverted the array elements and then I've used the same function, right? So that we don't have to write one more function, which is a modification of this, which instead of finding the maximum, finds the minimum. We have min here. Instead of doing that, I've simply inverted the array elements and then called this function. So what we do inside this loop, we compute the array sum, invert the array elements. Once the array elements are inverted, we find out the maximum sum in the subarray using the same function. So when you are finding out maximum sum in an inverted array, you are basically finding out minimum sum in your original array. So instead of subtracting the minimum sum, we add the maximum sum here because this is inverted. So we do minus minus, which becomes plus. And at the end, we simply return max normal and max circular. Let's see the working of this with this example. We'll get the max normal using simple cadence algorithm. We'll find out the max normal as 8, right, which is the maximum sum of any subarray in this, maximum sum of any normal subarray in this array. Now we run this loop, and inside this loop we find out the array sum. Array sum is 6, and in the same loop we invert the array. So what have we done? We have changed 8 to -8, -4 to 4, 3 to -3, -5 to 5, and 4 to -4. See, the reason for inverting this array is, as we discussed, we want to find out minimum sum subarray in this array. So minimum sum subarray in this array is going to be this. -4 plus 3 minus 5, which is -9 plus 6, -6. So to find out the subarray, we are using the same function. It's some tricky code where we are using the same function. We are simply inverting the array elements, and then we are calling the maximum sum. So once you invert this subarray, invert this whole array, you get this array. And now if you find out the maximum sum in this array, that will correspond to the minimum sum in this array. Right? Using the same cadence algorithm, we find out the maximum sum as 6. Right? So we find out maximum sum in this array using cadence algorithm, and we add it to the array sum. Our main target was to subtract this sum from the overall array sum. Since we inverted and found out the maximum sum, we are going to add that maximum sum instead of subtracting to the array sum. That's how we get the value 12. So 12 is maximum sum that you can get by considering circular elements, by considering the corner elements as contiguous. So at the end, you return the maximum of two values, max normal and max circular, which is 8 and 12 maximum. 8 and 12 maximum is 12, and 12 is our result. Now, one important thing about this implementation, this condition not only optimizes the code when everything is negative, it also makes the code correct. If everything is negative and if we remove this condition, then this code is going to fail. Let's see an example. So we have an array -5, -3. We'll get the max normal as -3. This algorithm will work fine, right? It will give you the normal maximum sum as -3. Now if we remove this condition, what will happen? What this part will compute? This part will first compute array sum as -11, then it will invert the array to 8, 3, and then it will compute the max circular as -11 plus 11 as 0. When everything is negative, this part is always going to give you max circular as 0, and which is going to be more than negative value that you got above. And then you are going to return the result as 0, which is incorrect for this particular example. So this particular if condition identifies that there is no normal subarray with sum 0 or more than 0. It means everything is negative. Don't proceed further and simply return the max normal that you have got. Let's now talk about the time complexity of the solution. We are calling a theta n function here first, so that takes theta n time. Then we are again doing theta n work, and then we are again calling theta n function. So we are doing theta n, theta n, theta n work 3 times. Overall time complexity is 3 times theta n, which is again theta n. So the time complexity of the solution is theta n.